we talked about the assumption of normality in our data and how skewness is calculated. This time, we're going to take a look at kurtosis. Kurtosis has a similar usefulness to skewness in that it tells us if our data comes from a normal distribution. If our data does not come from a normal distribution, we need to alter our statistical analysis path and the methods we use, because the majority of the analyses we use in multivariate or linear statistics have this assumption of normality, that things belong to a normal distribution. And so in kurtosis, we see two different types of distributions, or rather three really, if we take our middle distribution, but two sort of extreme versions of a normal distribution. The first is called a leptokurtic distribution. We'll underline that in green, box it in green even. So leptokurtic. So what does that look like? Well, lepto sort of means something like skinny or slim. And so it means that the middle part of our distribution is slim, skinny. So we're going to go ahead and see just how well I can draw a leptokurtic distribution for you. So we're going to end up with something like this. So you can see it's a normal distribution, but when we draw in our x-axis, you can see how this is different from a normal distribution. What we have here is we have very large tails. And so even though we have a normal distribution, it's sort of an odd one. Then over on the right side, we have what we call a platykurtic distribution. Again, we'll box that in green. Platykurtic is referring to a wide middle. So instead of this skinny middle with fat tails, we're going to have the inverse. We're going to have minimal tails and a very wide center. Inferences you can make from these is that a leptokurtic distribution, because it has more of the data out here, should have larger standard deviations. Whereas a platykurtic distribution, because so little of the data is out here, would have smaller standard deviations because everything is clustered closer to our mean, or rather to our measure of central tendency. So whatever the median is most likely. Now, we have one other type of distribution. We call it a mesokurtic distribution. This falls in between our other distributions of leptokurtic and platykurtic in that it shares some of the attributes of both. So we're going to have wider tails than a platykurtic, but a skinnier midpoint than a platykurtic, which means that we have, wait, got that backwards. We're going to have smaller tails than a leptokurtic, larger tails than a platykurtic, larger peak, larger middle than a leptokurtic, but a smaller middle than a platykurtic. We'll see if I can convey that in a drawing here. We're going to come up here. That seems okay. So you can see we still have our bell shape. It's not as wide as platykurtic, not as skinny as leptokurtic. Tails that are bigger than a platykurtic tail, we look here, but smaller than a leptokurtic. And again, this is just important because it tells us, or at least can help to tell us, if our data comes from a normal distribution and whether or not it's appropriate for us to use our standard analyses that we're going to get into later on in this channel. So, what's our formula for calculating kurtosis? Well, it's very similar to the formula we just did for skewness. We're going to have the sum of x minus mu, but this time we're going to take it to the fourth power. That is going to be over n times standard deviation to the fourth, and then we're going to subtract 3. And we'll get to why that's added in a moment. So let's go on and calculate kurtosis for our same data set. So first step, as always, when we see the sum of x minus mu, is we're going to go ahead and list out all of those variables so we can see our calculations. So we're going to have 3 minus 7 to the fourth plus 3 minus 7 to the fourth plus 5 minus 7 to the fourth plus 8 minus 7 to the fourth plus 10 minus 7 to the fourth plus 13 minus 7 to the fourth. And all of this is over 6, because we had 6 values, times 3.7 to the fourth. Bring some of this in to tell us we're on to our next step. Let's head on to step 2. Just like skewness, we're going to go ahead and take care of the inside of our parentheses. We're going to end up with negative 4 to the fourth plus negative 4 to the fourth plus negative 2 to the fourth plus 1 to the fourth. We'll just keep that in parentheses actually. Plus 3 to the fourth plus 6 to the fourth over 6 times 3.7 to the fourth. Now let's go on to the next page for the next 3 steps. We're going to take step 3, where we deal with all of our exponents. Now, since I didn't remember how to do cubes, that means I also don't remember how to do to the fourth. So we're going to take the values we had from before and use them as a starting point. And since we aren't on a negative exponent, we're on an even exponent, we know that our final result for each of these will be a positive number, so I don't have to worry about signs. So I'm going to have 64 times 4 is equal to 256 plus 256, because those numbers repeat, plus, well, we had 8, so 8 times 2 is 16. We'll skip the calculator for that. Plus 1 plus, let's see, 27 times 3 is equal to 81 plus, let's see, that was 216, yes, times 6 is equal to 1,296. All of this is over 6 times, let's see, we had 50.653 without rounding, and we'll multiply that by 3.7, our initial number, to give us 187.42 with some rounding. This takes us on to step 4. In step 4, we're going to add our numerator and multiply our denominator. So we're going to have 256 plus 256 plus 16 plus 1 plus 81 plus 1,296 is equal to 1,906 over 6 times 187.42 is equal to 1,124.52. So we get to keep all of that. Now, step 5, we're going to divide these. That's going to give us 1,906. 1,906 divided by 1,124.52 is equal to 1.69. Now, you might have noticed the last time I did this, but I've done it again. I have forgotten to carry on my 3 here. And I'm going to blame that on not having a whole lot of room to fit it over here. But at the end of each of these, we still have our -3. So we end up with 169. We'll zero the calculator so this matches up on paper with what I'm doing in the calculator. So if I ever need to replicate this, it's very important. 1.69 minus 3 gives us -1.31. So 6 steps in calculating kurtosis, only 5 in calculating skewness. So what does this mean? Well, when we're talking about the outcome of this calculation, we know that a positive number is telling us that we have a leptokurtic distribution, while a negative number tells us we have a platykurtic distribution. So if we come over here, this is telling us that we have smaller tails than a mesokurtic distribution or a leptokurtic distribution. Now, I am not familiar enough with the use of kurtosis to give you advice on at what point you start making changes to your analysis software or your analysis tools. So I'm just going to go ahead and leave you here with how it's been calculated. I hope this has been helpful for you and that you'll let me know if you have any questions or a suggestion for what you would like to see next is what would be helpful for you going through statistics or one of your other subjects in undergraduate or grad school.